Electrons possess an angular momentum known as spin, and they exhibit magnetic force in the direction of this spin. An electron can be thought of if an electron has angular momentum. One would expect every electron to maintain its own various spin directions, like a top maintaining a constant axial orientation. However, when a magnetic field is actually applied to measure the spin direction, it is found that only two directions can ever be measured relative to the direction of the field. This result remains the same regardless of which direction the magnetic field is applied. It makes electron spin seem like a physical quantity without a fixed reality that only takes shape upon measurement. Nevertheless, the reality of magnetic force in magnets is due to this very electron spin. Furthermore, while ordinary objects return to their original orientation after at least one full rotation, 360 degrees, an electron only returns to its original state after two full rotations, 720 degrees. This is called one-half-fold rotational symmetry. The half integer 1/2 in spin 1/2 indicates that the measured spin direction, magnetic direction, has only two possibilities and that it possesses one-half-fold rotational symmetry. Current physics explains these mysterious characteristics through the SU-2 symmetry of spacetime, but lacks an answer as to why the electron possesses that specific symmetry. In our space theory, these mysterious properties are explained by the precession and orbital revolution resulting from the combination of the three rotation vectors, angular momentum, that the electron possesses. Even though electron spin is only measured in two directions relative to the magnetic field, it cannot be measured using a standard, uniform magnetic field. In a field without a gradient, equal magnetic forces act on the N and S poles of the electron's magnet, causing it to press S like a top, but preventing it from moving in the direction of the applied field. In the Stern-Gerlach experiment, a special device was created where the shape of the magnets produces a magnetic field gradient depending on the position. The distance between the N and S poles relative to the field direction varies based on the orientation of the electron's magnet, the angle of precession. If there is a gradient, a difference in the magnitude of the magnetic force applied to each pole occurs, causing the electron to move in the direction of the applied magnetic field. First, a magnetic field is applied in the vertical direction, and electrons are passed through it. Silver atoms were used in the actual experiment. Before applying the magnetic force, the orientations of the electrons' magnets are random. Once the force is applied, the electrons press S like tops, but the angle of that precession should, classically, be random based on the electron's original orientation. If that were the case, the magnitude of the magnetic force would vary depending on the angle of precession and the orientation of the poles. Consequently, electrons should have spread out uniformly between the top and bottom of the observation screen in a fan-like distribution. However, the experiment showed that electrons split with a 50% probability of being up and a 50% probability of being down, with nothing observed in between. If electrons measured as up are measured again with a vertical magnetic field, they are observed as up with 100% probability, suggesting the spin is maintained. Next, if the up spins are immediately measured using a horizontal magnetic field, they do not travel straight through unaffected. Instead, the horizontal spin left/right is observed with a 50% probability of being left and 50% for right. Thus, despite being a form of angular momentum, electron spin direction changes depending on how it is measured. Our space theory explains the mechanism behind this mysterious electron top. In our space, an electron is a vortex of three rotation vectors, where a positive 2/3 charge and a negative 1/3 charge revolve around each other. Because the charges move in a circle, magnetic force is generated like an electromagnet. This is the nature of electron spin in our space, a charge top. Comparing a normal top to this electron top, when a normal top tilts, its center of gravity shifts away from the axis, and gravity acts as a force that tilts the axis further. In the electron top, charges are rotating. Since magnetic force is a function of charge, the force acts on the electron top's charges, serving as the force that tilts the axis. In a normal top, gravity always acts in the direction the axis is tilted. However, in the electron top, because the charges are rotating, the force is not always applied in the direction the axis is tilted. Therefore, the magnitude of the force applied to the axis changes periodically. If you apply a periodically changing force to the axis of a normal top, it begins to nutate, a motion where the angle of precession changes periodically. If the period of the applied force matches the period of nutation, the precession grows larger, the top becomes unstable, and it falls over. In contrast, in the electron top, the nutation actually decreases and the angle of precession becomes smaller. This is because the electron top possesses 1/2-fold rotational symmetry, requiring 720 degrees for one full cycle. Rotational symmetry refers to how many times a shape appears identical during one full 360 degrees rotation. For an equilateral triangle, rotating at 120 degrees makes it look the same as before. Since this happens 3 times in 360 degrees, it has 3-fold symmetry. A square has 4-fold symmetry. A complex shape that only looks the same after 360 degrees has 1-fold symmetry. Since 360 degrees divided by angle n degree to look the same equals n-fold symmetry, 1/2-fold symmetry means it must be rotated 720 degrees to return to its original appearance. While 1/2-fold symmetry does not exist on a 2D plane, Dirac's bell trick is an example. Additionally, if 2 coins are placed in contact and one is rolled around the other, the outer coin rotates 720 degrees to return to its original position, representing 1/2-fold rotational symmetry. As explained in Chapter 2 of the electron's 3 rotation vectors, x and y form a pair acting like a positive 2/3 charge, while the remaining z vector acts like a negative 1/3 charge. The rotation vectors x and y revolve around each other like a binary star system. Individually, however, the rotation vectors x and y are each a negative 1/3 charge according to the charge calculation formula. The trajectories of rotation vectors x and y result in a shape identical to the trajectory of the outer coin when 2 coins are rolled together. Rolling 2 coins in contact is a form of double rotation. In the electron top, vectors x and y pair up for 1 orbital revolution, rotation 1. And this pair then undergoes a second orbital revolution with vector z, rotation 2, creating a double rotation. Consequently, the charge of the electron top rotates with 1/2-fold symmetry. In normal rotation, 1-fold symmetry, a 360 degrees turn returns the object to its original state. If represented by phase signs, plus and minus, 0 degrees is plus, 180 degrees is minus, and 360 degrees returns to plus. In 1/2-fold symmetry, 0 degrees is plus, but 360 degrees is minus, and it only returns to plus at 720 degrees. In 1/2 fold symmetry, the sign reverses at 360 degrees. Because of this, the electron top receives magnetic force in a phase opposite to the phase of the spin axis precession. This acts as a force that cancels out nutation, causing the precession to decrease. The electron top possesses angular momentum, but due to 1/2 fold symmetry, the axis of the top, the axis of angular momentum, aligns with the direction of the applied magnetic field. Because the electron top rotates at incredible speeds, the axis orientation changes in an extremely short time, resulting in only 2 directions being observed along the measurement axis. Furthermore, the charge of the electron top fluctuates periodically in a direction perpendicular to the plane of rotation. Therefore, if it is remeasured in an orthogonal direction after being measured once, the periodic force acting on the charge will cause the axis to align either left or right. Whether it becomes left or right depends on the timing, phase of the rotation vectors, making a 50-50 probabilistic outcome. This is the reason why electron spin is always observed in only 2 directions in the Stern-Gerlach experiment, and it is the mechanism behind spin 1/2. The electron is a top made of vortices of angular momentum within our space. Because those vortices undergo double rotation, they react to external forces, magnetic force, differently than normal tops, which is why they appeared so mysterious.